Thank you for coming. Yeah, I'm going to talk about smart contract security. It's a big deal lately. In 2021, 1.3 billion were lost due to bugs in smart contracts. And so with that comes an entire industry around securing these smart contracts. So there's the auditing industry, which means that you essentially pay security experts to review your code, find any bugs in it, give you a report on how to fix it. And that gives you some assurance that you're less likely to be hacked. And then there's a second level of security, this kind of after auditing. Once it's already been deployed, there's security experts that do kind of freelance security checks, and they'll just read your code after deployment, try to find a bug, and then if they do, instead of stealing the money, they'll go to you in an ethical way and ask for a reasonable cut. And they've paid out, there's a bug bounty site, and they've paid out $62 million so far. So pretty intense amount of money at risk. What's that?
It's great. I like that kind of job.
Yeah, white hat hacking, yeah. Okay, yeah, and then I'm a program analysis person. So basically my expertise is building tools to analyze programs and find bugs in them. So there's like a whole bunch of different ways you can find bugs in programs. The industry is pretty mature right now for smart contracts. So you see things like the auditing industry. Basically, you have to pay security experts to review your code because these tools just aren't in a place that you can run them without having intimate security knowledge. Okay, so yeah, I'm going to go over 4 famous incidents that were either lots of funds lost. So the first is like the most famous one. It's the Dow. So this was in 2016. Can I see my notes somehow? All right, it's fine. It's fine. Yeah, that's cool.
Yeah, Google Slides doesn't really. Yeah,
Yeah, that's cool. Yeah, so the DAO was, I think, the first decentralized autonomous organization. So people were really like intrigued by this, and 14% of all the Ethereum on chain was invested into this DAO. So there were over 50 million in this smart contract. Now it would be 1 billion. And their contract wasn't audited, and it led to a massive bug because 14% of all tokens on chain were stored in this one contract and stolen. It had like a huge aftermath. Okay, so this bug that happened is now like a common pattern. It's called reentrancy. And this is how it works. So contract A is like our DAO contract. And when you do a call, this goes to the fallback function of a contract that the message.sender. So contract B is our message.sender. This is an attack contract which the exploiter has written. And so you can design this attack contract in a way to exploit this bug. So basically what you can do is the exploiter calls withdraw. Withdraw checks that they have enough money and sends the money to them. When that money is sent, it calls their fallback function. But they've defined this fallback function to also call withdraw. So what happens is it goes back into contract A. And at this point, notice that our balances were never updated. So we pass this check again. So like more concretely, if contract A starts with 100 ETH, and let's say contract B balances array has 20. So when we start with contract B and we call withdraw the first time, 80 is removed from contract A and 20 is removed from contract A and brought into contract B. So now we have 80 in contract A, but the balances mapping here isn't reduced until after this completes. So this line is never executed, and it keeps going back and forth like this. So basically, contract B can call this as many times as it wants until all the money in contract A is drained before this balance is ever updated. And so it always passes this check. Does that make sense? Yep. All right, cool. And so here's the actual code. This is kind of interesting. I'd never actually seen the code until I made these slides. So what happens here is that the first thing the attacker had to do was propose a split to the DAO, which was like a normal thing that happened. It went by. Usually people voted yes on this. Splits happened all the time. It was not anything exciting. But the wait period for everyone to vote on it was 1 week. So the attacker had to call this, wait 1 week until it passed this check. And then after that was satisfied, this goes to the funds to be moved, which calls this function create token proxy. And here's the pattern we saw, where it had a call and is sending the value to the attack contract, but the balances are updated afterwards. So that's the reentrancy pattern. And so now this is like a pattern security experts look out for. You shouldn't have any state changes after an external call. Hey. No. Yeah, so that's the reentrancy pattern. And then so like the effect that this one bug had on Ethereum was massive, because 14% of all Ether were stored in that contract. And so this is the letter that the attacker sent to the DAO and the Ethereum community. They said that they had carefully examined the code and decided to participate after finding this feature, where they were rewarded with additional Ether, and that they had made use of this feature and rightfully claimed 3 million ETH, and they would like to thank the DAO for this reward. And they go on to say that they're disappointed by those who characterize it as theft. And even on the DAO site, they say that the terms of the DAO are set forth in the smart contract existing on this address. Nothing guarantees anything beyond the DAO's code, basically. So this was like code is law. And but because 14% of all Ether was stored in this contract, the price of ETH like plummeted. So the Ethereum community had to like think really hard about what do we do here. And they actually ended up creating ETH dropped 25%. But yeah, they ended up reversing this, which you can't do because of immutability. But they essentially just created a new fork, and they called the old one Ethereum Classic, where the hacker stole the $50 million and just like skipped that block and continued on a new chain after they had fixed the bug. So this was like a huge debate. And I think one of the only times that this will ever happen. Yeah. So
was this considered a hack? Like, does the legal community think this is legal or no?
It's still a gray area.
Right. Does this apply to all smart contract hacking though?
So I think it's not illegal.
Not illegal.
Yes. Even people who do like white hat and gray hat hacking, it's kind of sketchy. Like it's a legal gray area right now, basically. Okay, so the next, that was 2016. So the next famous incident was one more recently, which is the Nomad Bridge. That's what's this summer, I think. I don't remember the month. No, the month was August. Okay. So $190 million were stolen from this one. This is a bridge, so bridges go between two chains, and they store a ton of funds in this contract because it is a bridge, and so they're really dangerous. So this is basically what Nomad does. Nomad is a protocol where you can send messages from one chain to another. And so basically you can implement a send function and a receive function, and your contracts will be able to either send or accept Nomad messages from other chains. So this is like a normal workflow. Say someone wants to send 1,000 USDC to the Moonbeam chain. It encodes the message that was sent in a Merkle tree, which is listened for off-chain. And then once the off-chain listener sees this update event occur, it goes ahead and relays that message to the movement chain. It checks to make sure that that message is actually in the Merkle tree that was encoded on the origin chain. So you can't just send messages to the receiver chain that didn't actually get sent from the sender chain. And then it gives the USDC. Yeah, but so basically, like, those coins are never actually transferred. What happens is the original USDC is stored in a Nomad contract on Ethereum, and then these like Nomad Moonbeam coins are also stored in a contract. So they're basically like holding your USDC as collateral and giving you this other coin on the other chain in return. But this leads to like a lot of funds being stored in the Nomad contracts, which is dangerous. Okay. Okay, so basically, this is how the hack happened. The hacker could send messages to the receiver contract that hadn't actually been sent from the sender contract. So when you send on the origin chain, we're holding that USDC as collateral. And then they're giving you out this other coin on the other chain. But if you can somehow get this Merkle tree validation to return true on the receiver chain, you can essentially get this coin for nothing because you haven't given anything on the origin chain. So that's how this happened. So here's the prove function, and it checks if it's an acceptable root. And the bug is that when they call initialize, they have, they set this, okay, sorry. When the developers for Nomad initialized this contract, they call this initialize function, and they passed in a committed root as the 0 address. So this is pre-approved the committed root. So confirm at the 0 address equals 1. So basically, sorry, this code is kind of confusing. But what happened was if you sent any message to the receiving chain and you sent it with the 0 address, it would look like you had actually put coins on the sender chain, and the Merkle proof would validate, and you would get your coin for free. I don't remember the code because I don't have the notes.
Question?
Yeah.
So is it just a bug in the design of the proof function for the?
No, so the proof function's fine, but what happened was here they do confirm at committed root always equals 1, and the committed root is 0. So they passed in like a special value to always be 1, and then so the attacker constructed a message where the Merkle tree root was 0, so that it's always proved. Yeah, so you could essentially send messages to the receiver chain without putting your own coins in as collateral and just take them on the receiving chain. And yeah, so then what happened was like complete chaos. The original attacker only stole like a couple 100,000, but then everyone else saw this happening and they just copy pasted the same message and sent it. Yeah, so there were like 400,000 people who split this $50 million basically. Some were white hats and they returned it. Some asked for a nice cut and others just stole it. But this was like called the largest crowdsourced hack. Yeah. Oh, yeah, and then there was like a huge debate over Nomad's security, because this was on their site where they said long-term security to do. And also they had gotten their contract audited by QuantStamp, which is like a pretty reputable auditing company. And they found this bug and they showed them that like you can initialize this with a 0 root in any provable pass. And they just like didn't fix it. So yeah, that's a problem. But I'm like not trying to trash Nomad, because these are like one of the first people who implemented like a bridge between chains, and things are bound to go wrong the first time anyone does something this new. But I think that the next time, the next generation of DeFi apps should put security first.
So like, when a smart contract gets audited by a firm and they don't find a bug that causes like a big issue, like in the past, has that like ruined the reputation of that auditing firm, or like people still trust them to like do work?
People still trust them. It happens a lot. So audits are considered time-boxed security reviews. You're not paying for them to find all the bugs. You're paying for their engineers to look at your code for a certain amount of time. So there's no insurance provided with that. And some people will get like audits from 3 companies, but they're also like crazy expensive. They're like $50,000 a week, depending on how big your contract is. But no, it's not their responsibility. I even saw one like developer give a talk where he injected bugs into a contract that were found during code review. And then he sent it to 5 auditing companies and like showed how many bugs each one found. And they missed a lot. Yeah.
Do you mind reiterating like how the bug works?
Yeah, sure. I'll just give you the breakdown without the code. But yeah, so what happens is on the sending chain, you send a message, it holds your USDC as collateral, and it encodes this message in a Merkle tree. Then on the receiving chain, we check that Merkle tree with the incoming message to make sure that it actually exists in this. So you can't just send messages that the receiving chain, which haven't actually been sent. And so there's this initialize function, which sets the confirm at the committed root equal to always true, pre-prove the committed root. And they called this with all zeros. You could see the transaction. So the attacker saw this transaction. They saw that a Merkle tree of all zeros is always confirmed.
Mhm.
And so if you send a message with the Merkle tree being all zeros, it'll confirm anything.
Yeah.
So they just said, send me like money to myself.
What's the intention of having that line in the initializer function?
Sometimes you want to do like, if you're an admin and you want to be able to perform, like, you want to have special privileges.
Right.
Yeah.
That's a terrible password.
Yeah. Especially since it's on chain.
Yeah, all zeros.
Okay, cool. The next one is Gym Network. This one is a Gym Network has anyone used Gym Network? Okay, cool. It's a DeFi aggregator investment system. I don't really know what that means, but I think that you can like just trade coins and farm. I don't know what that is either. But I guess it's a trading platform, and they have their own native token, GymNet. Okay. So basically they have this function, auto deposit, and it does a whole lot of things. When you call it, it's going to approve. So for token approval means that I'm allowing this contract to spend deposit amount tokens on my behalf. So that's what the approve does. And so then it sets a whole bunch of variables. It sets, this one's important, the deposit details, it sets the deposit tokens to the amount to deposit. And it does all this bookkeeping. but it never actually transfers the money. So it approves it, but we never see a transfer. So when auto deposit is called, all the state variables are set as if you actually did send money, but it was never actually transferred from your account to this contract. So then when you withdraw, there is a transfer and it sends you deposit details dot deposit tokens, which is the amount that was set here, even though you didn't actually send anything, and transfers it to you. So like that's pretty easy. You can just pull the money out. I think this was 21 million stolen. And yeah, 21 million, 2.1 million lost, sorry. And this was also audited. It was audited by 2 high quality firms, but they had updated their code 2 days later. So why carry out 2 audits if you're going to change the code base a month later? And this is just like a big issue with the auditing industry, because like I said, you're only paying for a time box review of the code. But like in any other industry, whenever code changes, tests run. There's like a whole infrastructure for continuous like runtime monitoring, continuous testing, and like every time you make a change, alarms go off. But you're not going to pay for another audit if you have to make a small fix. So that's basically what happened here. I have one more. Huh?
Yeah.
Okay, cool. The last one's Echo auction. If you're taking my class, you'll know this one. But this one I really like because it's like there's nothing fancy going on. It's just an auction, and it's just bugs in the code which cause this. I mean, I guess the other ones are too, but so the Echo Dreams, does anyone know about it? No, it's like a metaverse NFT project. This was actually on Time Magazine, and it was founded by an MLB player.
Nice.
So what happened here is that after the auction is completed, anyone who lost should be able to get a refund. So they had this process refunds function. And when you invoke it, it goes through all of the bids, and for all of them, it transfers the refund amount to the bidder. But all of this is done in a loop. And if a required fails and reverts, the entire function reverts. So imagine there's 100 people who bid. I'm the 6th person who bid. And I made this contract to bid with. So when this call happens, it calls my fallback function and always reverts. So everyone else can't get refunded anymore. Does that make sense? And I really like this one because they sent messages to each other on chain, which are kind of funny. So this was like a white hat hacker. They said, hey, there's a bug in your code. Your refunds will get stuck and you won't be able to achieve the rest of your funds. Do bug bounty on your contracts or have them audited. And then they didn't answer. And the hacker just kept sending messages. And at this point, I think the hacker actually tweeted, like, acknowledged that something is wrong, and they just said there's no bug. And then they sent this link, which was after they had placed a bid and the refunds could no longer go through, and everyone was freaking out because they couldn't get their money back. But luckily, this hacker was white hat, so they had actually made their exploit contract with a block boolean, so that they could unblock all the funds, set block to true, and then whenever call invoke their fallback function, it could either revert or succeed. And then, yeah, once they had unlocked it, they said, well, this was fun. I had no intention of actually exploiting this. Once you publicly acknowledge that it exists, I'll remove the block. And then they unlocked it. There was actually another bug that unrelated to the attack, and they still, all the bidders got their funds back, but the money that the auction made, like the money that the winner had put in, they could never retrieve it because of a different bug. So at least all the users got their money back, but the contract creators and NFT creators still got nothing. But that was an unrelated bug. Okay, so you're probably like, I am scared to build smart contracts because they're all gonna get hacked. What you can do to prevent this, the first is study classes of vulnerabilities like reentrancy. If you know what to look out for when you're coding, you'll write much more secure code. Second is to write specifications and run automated tooling. If you write down in logic how your code should behave, that right there will get you really far. Because you'll find spots in your code where it's not conforming to what you had expected. And then once you have those logical specifications, you can run automated tooling. And there's also nice automated tooling out there. You can do testing, you can do formal verification. And all of these things will provide you with higher quality assurance that your contract's not going to get hacked. And then if maybe you're not a security expert and you're still nervous, you can get your code audited. But again, there's problems with that, other than it being expensive. After deployment, you should still be testing and monitoring, especially if you're upgrading your code. In general, like software practices before Web3 should still be used during Web3. Like in internships at like Microsoft or Google, you don't just write the code and put it out there. You should do code reviews, you should run tooling, you should have continuous integration, and you should always be concerned about correctness. And then lastly, there's bug bounties. Like this is like a last ditch effort. You just put it on a bug bounty site and then just hope that if anyone finds the bug, they'll go to you and you'll pay them like 10–20% and no one will hack you. I think that was it. I went really fast.
Do you do bug bounties before or after launch?
After.
But then people can actually hack it,
Yeah,
right? Because like there's already value in the contracts.
exactly. So bug bounty is just like, I'm putting it out there, but I'm also listing it on this bug bounty site. So if someone finds the bug and they're scared about like stealing it, then they can come to me, do the right thing, and I'll reward them. And it's also like, there's so much code being deployed that the amount of people with the security knowledge and mindset can't look at it all. So if you want someone to look at your code, you should post it on the bug bounty site. Because a lot of people just do this in their spare time because of how huge the bounties are. Hundreds of millions.
Can you talk a bit more about the automated tooling system? I think that'll be something people will be interested to learn more about.
Yeah, sure. There's lots of different classes of automated tooling. So first, I'll go from easiest to use but lowest security assurance to hardest to use but highest security assurance. Easiest to use is testing. Like everyone can write unit tests. You just write down the sequence of calls and how you expect the code to behave. You do that on concrete inputs though. So you might say if I deposit 1 ETH and I withdraw 1 ETH, there should be the same amount in my account as when I started or something. But then you're only testing very specific values. So the next step for higher assurance is fuzzing. This is automated randomized testing. So instead of having concrete values, you ask the tool to randomly inject them. So you can say, if I deposit some random number of ETH and I withdraw some random number of ETH, then I should have the same amount as the beginning. And that provides you higher quality assurance because devs will only think of cases that they're expecting. And so fuzzing is really good at finding these kinds of bugs. Fuzzing can also randomize which sequences of calls to make. So maybe there's some wacky sequence, like if you call withdraw without calling deposit, you can just get the money. Like the dev would never write a test for just withdrawing. So fuzzing can help you there too. And so that gives you higher assurance than just plain unit testing, because you're testing these different values and these different sequences of calls. But it doesn't give you super high quality assurance, because we can't check every input. Unless we run for infinity, we'll never be able to hit. There's still a chance that we just haven't found some input that's the exploitable one. But fuzzing's still pretty easy to use, run, but it provides you some more quality assurance. Yeah.
So I feel like it's pretty hard to write bug oracles for fuzzing. For example, the auditing contests that we're doing, I don't even know how things could fail and what counts as getting hacked. I mean, it's easy. I guess like we took the approach of just looking through the code and use the other testing tools, just because fuzzing is so hard to write, and sometimes the characterization of a hack requires sort of going through multiple steps. Like, you know, when someone is the owner, and then they, you know, try to, or when someone is not the owner and they try to transfer NFT and it should not go through, right? Like that's really hard to write as a fuzzing oracle. Like how would you approach that?
So there are some general purpose oracles. This is in general a really big issue in smart contracts though. In languages like C, you can just say there should never be a set fault.
Right.
That's what fuzzers check for, memory errors, but they don't have that in smart contracts. But still, there's some best effort generalized oracles. Mithril, which was homework 4, has them. So there was like ether leaking. So you should never be able to withdraw more funds from a contract than you put in. Like that's a pretty general one.
Right.
Or like ownership escalation. Only the owner should be able to make someone else owner. Like those things are pretty general purpose.
Got it.
And hopefully the tooling will improve such that the amount of setup for a fuzzer is much less, and that these oracles will be automatically injected.
Is there like a marketplace or, you know, a place where people are actively contributing, you know, these generalizable fuzzing tests? What do you think is the best? Is there an ecosystem, like specific ecosystem that's the best that people are using?
For fuzzing,
Fuzzing,
there's 2 fuzzers. Echidna's one. The other one is Foundry.
right?
Neither of them provide bug oracles, and neither of them are easy to set up for people who aren't security engineers.
So market opportunities.
Yes. Exactly.
Nice. Pay attention.
Yeah. Yeah, but in general, the industry is kind of focused on auditing. So all of these tools are coming out of auditing companies. So they're building things to help auditors. They're not concerned with helping developers. And so the issue with the security tooling is they require security expertise.
Right.
And hopefully we'll get to a point where developers can use them. And then hopefully we can get to a point where you won't even need to read and understand the code. You can just run a tool and it can find a bug.
Right.
Because that's how it's like for C. In like capture the flags and stuff that have like extremely obfuscated code on purpose. So you can't even read that. You're not going to read through every line and write specs. You just run a tool out the box and it finds memory crashes.
Right.
And when that exists for smart contracts, it's going to be crazy.
What do you think are the best efforts, you know, going in that direction? It's these, is it these like existing tools?
No, I don't think either of those are going to build with developers in mind.
Right.
Yeah, in general, developer tooling for this space is really bad. And I hope it gets better. But yeah, I really like testing. But after testing, there's other tools which provide you with more assurance. So there's symbolic execution. Symbolic execution is like fuzzing, but the inputs are not random. The inputs are generated such that you only execute each path through the program once. So instead of generating 1 million inputs, which all take the same path, okay, now we've wasted 999,000 cycles. In symbolic execution, each input corresponds to exactly one path in the program. Unfortunately, finding those inputs is extremely slow. It is automated, but symbolic execution can take hours for very small contracts. And you have the same bug oracle problem that you do with fuzzing, but it does provide much more assurance. Because you've executed every single path in the program, you have more assurance from randomized testing that you'll find a bug. And then the largest extreme of hardest to use, but highest assurance is formal verification. Formal verification is interesting because you treat the program as a mathematical object and get a proof that some bug will never occur. It's extremely difficult to write these specifications. And in most normal software engineering, it hasn't taken off. Formal verification's only like really been big in like verifying automobiles and medical devices and airplanes, but the amount of cost that it is for normal software, it's never been invested in heavily. But it's really booming in the smart contract industry because of the financial cost of each bug. And there are quite a few formal verification auditing companies coming out now. And yeah, so it provides a huge amount of assurance, but the issue is it's only as good as the specs you write. So first of all, you have to write extremely good, high quality specs, which only security engineers can know how to write. And representing the program as a mathematical object has quite a few challenges. So there is a company called Certora. They're going to have a guest lecture in our course, but they're probably the biggest formal verification auditing company. And they are trying to train developers to use this tool themselves. So we'll see how that plays out. It will be really interesting because I think it would be one of the first real developer formal verification tools. I'm not sure of any other scenario where developers are formally verifying their own code. Has anyone done that before? Everyone tests their code, right?
Sure.
Just like in general, does anyone fuzz their code? Or do you all just like stop at unit tests?
Wait, how do you fuzz, like, how do you do that?
There's tools.
Oh,
for it.
it's a, like, you down specific tool.
Yeah.
Oh, okay.
Yeah, so like, I guess that says it right there, that nobody is willing to use these very high assurance tooling, which is understandable. And perhaps formal verification auditing companies will still be really important, but the lower assurance ones can be put in the hands of the developers. I think all of these bugs could be found with fuzzing, except for the last one, because that's a locked funds. But I think all of these other bugs could have been found with fuzzing with a ether leaking oracle, meaning that you can't withdraw more funds than you put in. First one couldn't be found with the fuzzer either.
Yeah, I guess I wonder if there's just a really easy tool, because even right now, like fuzzing is really, it's not very straightforward. There just needs to be like one click installation for you to, do security testing, even very elementary security testing. That would cover, as like in terms of the number of developers, I would say like 90% of them are bad developers, and that'll cover the 90% case, and they would feel pretty proud to say, I did my quote unquote testing, but it's better than nothing.
Yeah, I mean, there's a number of challenges for it, but I think they're all solvable to make this extremely automated. Yeah.
Let's say you like the bug bounty people find a bug. I mean, clearly that's something that exists out there, and that's an exploit like anyone can have a look at. Like that they can exploit, like it's still in real time. So like, what's the next steps for the organization in whose smart contract the bug was found? Like, do they shut down the contract? Because I mean, that'll have a lot of implications, I'm sure. And like, how exactly do they update the contract?
Yeah, good point. So most of these contracts, like you've probably heard that they're immutable, that it can't be updated. But what people do now is almost never immutable. What they do is they have a proxy contract. And so any transactions that happen go through this proxy contract. And then those get transferred to their implementation contract. So then if they want to change their implementation contract, they just swap out a value in the proxy contract and now it goes to another one. So that original contract still exists, but you can route your new request to a new one. As for like the bug bounties getting paid, there's a centralized third party called Immunify. And if you find a bug, you go to Immunify, you tell them, you show them the steps to like execute that hack, and they show the company. Once the parties have agreed, they pay you 10% of whatever you could have stolen. And then if they don't pay you, maybe you go exploit it anyway.
So what does Immunify get out of that? Like just a commission fee or something?
Yeah.
Oh, it's very smart.
They also get like a few percentage points.
I think they get 10 too, actually.
Oh,
Yeah. So hopefully there'll be a smart contract version that's decentralized where you can just submit your POC of the steps to hack it. And the only person that'll have to get paid is you.
it's gonna be a zero knowledge proof.
Yeah, actually.
It'll have to be.
Yeah.
Wow, this is fascinating. Hackathon project, guys, take notes.
Yeah, someone should do that.
Any more questions? Think we're good?
Nice.
Oh.
Are there questions in the Zoom?
No, those are just my messages.
Intel 6 and so many people.
All your accounts.
Yeah. Okay, cool. I'll stop the recording.
Thank you.
Thank you.